Thank you, Mr. Chair, and good morning, everyone. The work that I'm going to present to you today is about a machine learning-based multi-scale modeling approach for the damage analysis in bioinspired composite structures. But first, please let me thank my co-authors from University of Calabria, Domenico Ammendolea, Fabrizio Greco, Paolo Lonetti, Paolo Nevone Blasi, and Girolamo Sgambitterra. So let's start with the motivation of this work. It is well known that bioinspired microstructures possess very exceptional mechanical and functional properties, which are essentially due to their optimal combination in stiffness, strength, and toughness. However, such materials may experience some complex failure phenomena, fracture phenomena, which are intrinsically related to their intricate microstructure. It is recognized that numerical models are nowadays fundamental tools for the optimal mechanical design of this material. Among the existing numerical models, multi-scale models have emerged in the past decades as reliable approaches for analyzing failure phenomena in various classes of composite structures and also in bioinspired ones, by virtue of their optimal combination, optimal compromise between numerical accuracy and computational efficiency. So most of the recent multi-scale models are applied within the framework of nonlinear computational homogenization approaches. Just let me recall the most recent one that are data-driven numerical homogenization approaches. These approaches are very fast, are very efficient, because the physics-based constitutive relations are replaced by a regression and machine learning algorithms to predict the homogenized behavior of this material. But currently, there are some limitations for this model because essentially related to the difficulty in defining appropriate internal variable for material characterized by a strong history dependence. So this is an open issue. So in this work, we want to propose a new enhanced data-driven multi-scale model for managing, for analyzing failure mechanisms in composite structures, and in particular, we want to apply this model to a particular kind of bioinspired structures that is nacre-like one, so inspired by nacre, natural nacre. So this is an example of microscopic modeling of nacre-like structures. So here we will model such material as staggered composite composed of discontinuous reinforcement in the form of hard platelets dispersed, so embedded in a soft matrix according to a brick and mortar arrangement, so masonry-like arrangement. In particular, a simplified micromodel will be considered with expanded platelets and matrix joints lumped into zero-thickness cohesive interfaces. These embedded interfaces are equipped with a traction separation law, which account for fracture onset and propagation under mixed mode loading conditions. Conversely, at the macroscopic scale, nacre-like composites are modeled as anisotropic homogeneous material. So they possess a nonlinear anisotropic constitutive behavior, which has to be homogenized in some kind. using some kind of homogenization method. So in the present work, we assume the existence of a strain energy function also in the damaged configuration, that is at fixed damage, in such a way, at most 21 components, independent damage elastic constants will be used for modeling a truly anisotropic behavior. As a main hypothesis of the present approach, the damaged elastic moduli tensor itself plays the role of tensorial damage variable. And this internal variable, this state variable, has to fulfill the damage dissipation inequality for assuring the thermodynamic consistency. And also loading and unloading condition must be satisfied. These loading conditions are expressed in terms of the well-known Karush-Kantaker conditions. So, in this slide, I want to recall briefly the main extended micromechanical relations which were used in the homogenization steps. These extended relations explicitly account for the elastic contribution of embedded interfaces at the microscopic scale. In particular, due to the brick and mortar arrangement, this material is considered as periodic, so that a repeating unit cell is chosen as a representative volume element for homogenization purposes. So it is worth noting that in the present first order homogenization scheme, the homogenized behavior retains a local character, but there is a limitation for softening microstructures. So some kind of regularization is required to ensure objective structural responses. In this work, we try to apply a coupled volume homogenization scheme originally proposed by Gitman and co-authors to obtain objective homogenized responses also in the presence of strain localization phenomena. In this enhanced scheme, the macroscale mesh size and the RV size are uniquely linked to each other, so to avoid the mesh size dependence for structural scale analysis. So let's move to the brief description of the proposed data-driven multi-scale approach for staggered composites. So this approach consists of two phases, the offline phase and the online one. The first one consists in the derivation of a complete anisotropic damage evolution law at the material level, so the micro scale. And the second one is devoted to the prediction of the failure phenomena of damaging composites at the structural scale, so the macro scale. In the offline phase, we perform a two-step finite element approach for computing sequentially the principal path solutions for different proportional microstrain histories and the auxiliary solution required to compute to determine the homogenized elastic moduli at fixed damage. So to this end, we consider a repeating unit cell. We apply several microstrain histories, which are proportional histories, and these histories are parameterized by using spherical coordinates in the 3D microstrain space when applied to a 2D setting, to a 2D finite element setting. Once derived the microscopic second moduli by standard homogenization approaches, we use a deep neural network to compute, to derive a damage type surrogate model to predict damage starting from the micromechanical data obtained in the first step. So once trained, this neural network is capable to use as input the microstrain tensor components to predict the overall moduli tensor components, the 6 moduli in the 2D settings. Obviously, this surrogate model does not fulfill a priori the damage reversibility, which is required for thermodynamic consistency. So in this work, we try to apply in the subsequent online phase a new stress update algorithm, which is able to handle elastic unloading while enforcing damage reversibility. So how it works, this approach? So the stress update algorithm consists in a predictor step in which the trial moduli tensor is predicted directly by the deep neural network. And then in the subsequent corrector step, we try to correct the moduli to enforce the incremental damage dissipation inequality only if this relation is violated at each step. So let's move to the numerical experiments performed to validate this approach. This is an acrylite composite. You can see the geometry, the finite element mesh, the elastic and the inelastic parameters for the embedded interfaces. We performed the micromechanical homogenization steps, and then we try to train the deep neural network using these hyperparameters. And here you can see the final values of the validation and training losses. So in this slide, you can see the evolution of the macro scale moduli components as a function of the applied microstress. And these data, these are micromechanical data which are used in the training phases. In particular, you can see that in the combined shear biaxial path, the initial orthotropy exhibited by necrolac is lost during damage evolution. So this confirms the capability of the modeling to simulate full anisotropic behavior. And then we move to the validation step of the proposed data-driven approach. This validation is made by comparison between the data-driven and the standard micromechanical homogenization for different loading histories. Let's begin with monotonic proportional loading paths. In particular, for purely biaxial loading paths, you can see clearly these are stress-strain curves at the macro scale predicted by the two approaches. They agree with each other for different applied microstrain histories. So this is for biaxial loading path. This is for shear biaxial path, so combined paths. And you can see a substantial accordance between the two families of curves. So the proposed approach is confirmed to be very accurate from a numerical point of view. But for a deeper comparison, you can see also the errors between the two analyses expressed in terms of the maximum effective macro stress, so the peak stress. The maximum error is about 2.5%, and the average error is of about 1% for all the applied microstrain histories. So the approach is fully reliable and very, very accurate. A further validation is devoted to non-monotonic proportional loading path. In this slide, you can see the capability of the proposed approach to perform also the unloading, to predict the unloading in a very accurate manner. This is due to the capability of the stress update algorithm to correct the damaged moduli tensor when unloading takes place. And then the final validation, you can see the comparison between the two approaches for non-proportional loading path. This is the most important validation because these paths are not seen by the deep neural network. So there are new paths which are not used in the training phase. These paths are two-step paths. In particular, I'll show you only 4 paths. P1 is a two-step loading. So first tension, then shear loading. The second one, first shear and then tension along the horizontal direction. P3, shear and compression. P4, first compression, then shear. So these complicated paths are a stronger validation for our approach. However, a reduced accuracy can be seen in these slides. So the results are quite good, but there are some discrepancies. The error here is about 9%, and also you can see discontinuities in the predicted response by the data-driven approach. So, in conclusion, I have presented you today a novel, efficient, computationally efficient, data-driven multi-scale model for the damage evolution analysis in bioinspired composite materials, based on a deep neural network surrogate model for deriving the homogenized response of the composite, so the homogenized damage moduli tensor. The validity of the present strategy has been shown by performing several comparisons with the direct micromechanical analysis for several loading paths, also including non-proportional loading paths. So, in summary, the present results have confirmed that the data-driven multi-scale approach has some advantages. First of all, high computational efficiency. I didn't report the computational times, but we can say that multi-scale failure problems are solved at the cost of purely macro-scale ones. So without the requiring to perform a repeating unit cell analysis. High numerical accuracy. I have already shown you the overall stress strain curves, but also the great ability to handle loading proportional macro strain paths. This is due to the explicit enforcement of damage reversibility condition by virtue of the proposed stress update algorithm. But also there are some limitations of the proposed approach. I have shown you that for non-proportional loadings, we reported a reduced accuracy, especially when damage growth is strongly dependent on the application loading order, loading application order. So just let me show you some possible future perspective of this work. So first of all, an enhancement of the present strategy to properly handling also general non-proportional loading path. And a possible way is to include the non-proportional microstrain path in the training phase for the deep neural network. This is a work in progress. And then another possible perspective is the inclusion of large deformation in the finite element settings. This could allow us to investigate the interaction between fracture and instability phenomena in bioinspired composites, which is a very common feature for this kind of material, so in particular for nacre-like ones. So I thank you for your attention.